Okay, so last time I accidentally pushed stop record last time, so it kind of cut me off there at the last second, so sorry, apologize about that. And so, but we just got done going through the Wilson cycle, right? Okay, of how the Wilson cycle occurred in North America. It's pretty cool, actually. At least I think it is. It gives us an understanding really better of what happened in our past and really what geologists are trying to do. They're trying to look at the past and look at the past climate to be able to understand what's going to happen in the future. So this is kind of a review statement, just going to help us at the outside. Which of the following statements concerning the forces that drive plate tectonic motions is correct? Plate motion movement occurs primarily because of simple convection cells in the mantle. That is partially true, where convection cells actually start this off. They initiate the bit, but they don't drive it, right? So movement of oceanic currents causes the overlying plates to move. That's not strong enough. Ridge push and pull forces have the greatest influence on the velocity of the plate motion, and that's absolutely true. Okay, and so the last one is one that actually Alfred Wegener tried to put in as his mechanism, but it's just not possible. The forces are not strong enough. Okay, so let's go through each of these boundaries a little bit better to be able to understand what's going on here. Okay, so we're going to first talk about divergent boundaries and the different types of divergent boundaries. Okay, the first one is that we're going to kind of focus on is a divergent boundary within an ocean. Okay, these are the simplest ones for us to understand. They're the ones that this is the one that's off our coast. Okay, this is a cross section of the ocean floor from the continental shelf of South America all the way to the continental shelf of Africa. Okay, so it's pretty much a line going across this area here. And what you'll notice as you go across, there's what we have the shelf. Okay, that's still underwater. And then you go down into the continental slope, which is this right here. This is all continental crust still. And down here this is oceanic crust. This oceanic crust is what we call the abyssal plain. The abyssal plain, I say that wrong all the time. The abyssal plain, and then you go all the way up to the ridge axis of the Midocean Ridge. Now remember, this is when the material from down below is pushing up on the crust, causing this to be higher elevation right here. And then it goes back down. Now it goes back down because here it's hot, but as it goes away, it cools off to form this denser material down here in the abyssal plain. And it goes back up to the continental shelf. So you'll look down here. Here's the bathymetric map of the Mid-Atlantic Ridge. Here's the high point as you go from the ridges across. Then we have what we call the divergent boundary where it's going apart. Okay, moving in this area about 1.7 centimeters per year. Pretty slow. Okay, as you go through those areas. Now we call this edge a passive continental margin because there's no activity here. There's no volcanic activity here, and there's no earthquakes here. Well, there are earthquakes, but they're rare. Okay, just like here in North Carolina, there are earthquakes, but they're rare earthquakes because there's still pressure. The oceanic crust is still pushing on that continental crust. So there's still pressure being exerted in this, and so we can still have earthquakes, but they're rare. They don't happen very often. If you actually had it dive down or break off and then go down, then you'd have lots more earthquakes. We'll talk about that convergent boundaries a little bit later. Okay, so good. So in the mid-ocean ridge, you have that material rising up, pushing up the crust, and starting to form different kind of features. Now on the bottom, it's the lithosphere here. Then you have the gabbro. If you remember in our igneous rocks, gabbro is intrusive mafic material. Now remember, the asthenosphere is ultramafic. It's just because it's denser, right? It's going to float at the bottom. And it's going to be hot, melts up as it cools off. That mafic stuff is going to form off here, and then it will come up slowly, break apart the rigid stuff at the top, forming a bunch of faults. And if you remember in our pillow basalts, that's when you have that lava cools off in water to form these, we call these ridges across here. Now, different ages of rocks will have different magnetics associated with it. So as you push on that, the magnetics in that rock might point to the north. And over time, sometimes you might not know this, but sometimes our North Pole actually flips, where the North Pole becomes the South Pole and so forth. The whole planet doesn't flip, but the electromagnetic field flips. Okay, and as it does so, if you have a rock actually come out during that time where it was flipped, the magnetic rocks would actually point to the south. Okay, and then it would go back, point to the north again, and so we have what we call these these age differences because of paleomagnetics. This is one of the reasons why we knew that the plates were actually moving, was because we saw these bands of different magnetics inside the ocean floor. Okay, so notice that the lithosphere actually thickens as you go away from the center. Now, it's actually melting here because remember, as it rises, it's being decompressed, therefore the magma is actually forming, right? And then as it goes up, it will push apart. It's what we call ridge push. But as it goes away, it's going to actually cool off. So as it cools off, it becomes thicker. This area here, the stuff down below, gets stuck to the bottom of the lithosphere, and therefore it becomes thicker. So here it's more buoyant, partly because it's hotter, but also because it's not as heavy. Okay, so it rises higher in the water. When as it goes away, it cools off, so it gets denser because it's cold, but it's also getting denser because it's thicker. Okay, so that's important. Now, we'll keep that in mind because we're going to talk about this when we talk about convergent plate boundaries later. Okay, and how that actually this idea of how it becomes thicker as it goes away is important in understanding convergent boundaries a little later. Okay, let's keep going here for a second. So let's say this rising, decompressing magma came up underneath a continent. Now we don't really know why they all of a sudden start and form. That's one of those things that we still haven't figured out yet, and you'd probably be really famous if you ever did. Okay, the point comes here though is we really don't know yet. But when it does happen, when that magma comes up from down below, it's going to start to thin out the crust. So I'm going to get my silly putty here again. Okay, get it here. Let me get it thicker here. Okay, so here we go. So here's this silly putty, and it's this nice thickness of it. Now if I push on it from below, it's going to actually dome up like this, right? Okay, it's going to initially dome. So you have these upwarping that you have here. And you actually can see this in Africa. In Africa, you have these areas where you have this updoming. The Kenyan dome, the Ethiopian dome is all this magma from down below pushing up on the crust as it's rising. Okay? Now, as you continue to rise, it's going to start to pull it apart. And as you pull it apart, the crust is going to get thinner. And at some point, that it can get so thin that it actually cracks. Okay? And then magma can come up into that. So we can get these valleys, these rift valleys here, where we have shield volcanoes forming all up and down that valley. Okay. Now, if you keep going, at some point, it's going to continue to break apart until it's all the way broken. And now you're going away only forming oceanic crust down here at the bottom. So that's a great example of here in the Red Sea up here, where it's actually pulled apart enough that the ocean water is flooded in, forming actual oceanic crust in the middle of the Red Sea. Okay. So that would be our nice linear sea. Great examples of this linear sea, Red Sea. Okay, good example of a continental divergent boundary, the East African Rift. It's probably one of the best ones in the world. Now, if it kept going, you'd have a ridge in the middle with two passive margins on the sides. Okay, like North America and Europe, or South America and Africa. Right. So here's some examples. Right now, currently, this is happening today here in East Africa. Still in East Africa. This is now occurring here in the Red Sea. This current one is occurring in the Atlantic Ocean. Great examples of all of these. This would be what we call a continental divergence. This is what we would call an oceanic divergence. Okay. So here's some other examples of some divergent boundaries around the world. We talked about the Gulf of Suez. This is the Red Sea. If you keep going to the north, you have the Gulf of Suez and the Gulf of Aqaba, and those are both divergent plate boundaries as well. They're starting to pull apart. If you keep going up, that actual divergent boundary goes right through Israel. This is why we have the Dead Sea there in Israel, because it's so low. Okay, and the Gulf of Suez goes right through here, and they did the Suez Canal to connect those, but in the future, it might go apart anyways, right? Okay, another one. Here is the Gulf of California, where it's being torn apart down here in the California, okay, forming what we call the Baja California. This is the peninsula of California. And it's causing it to the whole thing to slide this way, causing the San Andreas Fault up here, okay? Iceland is another example of a mid-Atlantic ridge. It's a connection of the Mid-Atlantic Ridge. this section is a little hotter than the rest of the Atlantic Ridge, and so therefore it's actually, the magma has actually reached the surface, and now we actually have land there that forms. So we actually have volcanoes forming off the coast sometimes of Iceland in just the last 10, 20 years. Okay, they're actually forming off the coast. And here's some of the examples of the rift valleys inside of Iceland. The same thing's happening a little bit in the western United States. The western United States is slowly being pulled apart. So it has to do a lot with the same divergent boundary that was down here. It's slowly pulling apart North America, okay, forming these mountains that are forming all north-south. So basically, I'm going to look at these mountains here. So as they pull apart, they're forming these basins. We have mountains, basin, mountain. Mountains, basin, mountain. We call that the basin and range of the western United States. And later in time, maybe 10 million years from now, that might actually be cut off from the rest of the western United States. Okay? Okay. So that's examples of divergent boundaries. Let's go to convergent boundaries now. Now remember, there's two types of crust, oceanic crust or continental crust. If there's two types of crust, then that means there can be three types of convergent boundaries. Okay? So the important densities to remember, and I don't care about the numbers, you do need to know the relative densities of them, all right? So continental crust is that felsic material. Felsic and intermediate material of the magmas. It has a lower density, therefore it's going to ride higher on, like if you had a boat that was less dense, it's going to ride higher, okay? Whereas your oceanic crust is going to ride lower because it's mostly iron and magnesium, okay? Whereas the felsic material is mostly silica and aluminum, okay? And then the asthenosphere is even more mafic. Remember, that's what we call ultramafic, and therefore it's even denser. So the asthenosphere is always going to be at the bottom. The oceanic crust is going to be above the asthenosphere, and so is the continental crust going to be above the asthenosphere. But when the continental crust, which I always specify as a fish because it's thicker, and the oceanic crust is always thinner, so therefore I specify it as my flat hand, if they come together, what's going to happen? Well, this one's denser, even though it's thinner, because it's made up of the mafic material, and it's going to go down, okay? So we call this an oceanic continental convergence. A good example of this today is Peru and Chile, okay? This is happening in a lot of places. It's happening in Japan. It's happening in, not Japan, that wasn't a good explanation. It's happening in, in Italy, okay, where the African plate is going underneath the European plate, okay? It's happening in Alaska, where the Pacific plate is going underneath the North American plate. It's happening in South America, where the Nazca plate is going underneath the South American plate, all forming these chains of mountains and volcanoes. In the southern United States, southern hemisphere, in South America, it's forming the Andes. Okay? Now, what if I had two continental plates coming together? Now, both of them have the lower densities, right? So if they both have the lower densities, neither one of them are so dense that they're going to actually go down into the asthenosphere. So they stack up on top of each other. Okay, they'll stack up on top of each other and form what we call a continental convergence. Okay, the last one that we have, okay, and a good example of that, is India, where India is slamming into to Asia, Eurasia, forming the Himalayas. Okay, the last one is when we have two oceanic crusts and they come together and slam in together, and one of them will go down. Now, if the oceanic crusts are the same density, why is one going down? Well, it goes back to this idea that we talked about just a second ago. Okay, where closer you are to the divergent plate boundary, the thinner the crust, and therefore the lower the density. The further away from the divergent plate boundary, the more dense it is. So if you go back to this, when we have these three types, the oceanic convergence, the crust that's further away from a divergent source, where that material is being formed, is going to be colder and older, and therefore denser and thicker. So therefore, that's the plate that's going to go down. If that plate goes down, it will then melt as it goes down, forming volcanic islands or volcanic island arc to form more continental crust. Kind of cool. Anyways,